Okay, we can see it.
Okay, so let me proceed by previously we have talked the first 2 weeks ago we talked about the process involved in cross-cloud validation. We described what machine learning is and what processes are involved in machine learning. And last week we looked at another aspect, talking about the regularized regression, the lasso bridge.
We
This,
can't hear.
you can't hear me. Can you hear me? Can you hear me?
Yes, please just move to where you can have your strong network. We can hear you.
We can hear you.
We can hear
you're
you.
fine.
Okay, good. Yes, so today we are looking at the support vectors machine. And the outline is as provided. We are going to be looking at the introduction aspects, maximum margin classifier, support vector classifier, support vector machine, support vector regression, and the house scripts are also provided for the lab session. So today we are going to be talking about the theoretical background that relates to what you are going to be doing in the lab session. Then we look at, we simulate data, and also we use a real data, or we can call it live data, that is provided in R to demonstrate what we have talked about. Now, looking at maximum margin classifier. Now, we know that the parameters of the linear regression, we know we have B0, B1 up to B sub P, depending on the how long P is. And for a P-dimensional hyperplane, we can be expressed as equation 1, and the value of the left-hand side will determine the side of the hyperplane that our equation on the left-hand side belongs to. So if it's greater than 0, is on one side, and if it's less than 0, which is negative value, is on the side of a hyperplane. So I think that particular slide has been explained. So if you have any further questions, you can ask. Now we go, this is just a graphical representation of example of what's been discussed. Now, assuming we have 1x, 1 plus 2x1 plus 3x2, if this value, the ones that greater than 1, that the other upper part, and if it happens that the region that is less than 1 is the lower one. Okay. Now, we look at the maximum margin classifier. Now, this particular classifier, it separates hyperplane for which the margin is the largest. So it is the hyperplane that has the farthest minimum distance to the training observation. The first class, we talked about the training observation, and we have the testing data. So now this maximum margin hyperplane is the separating hyperplane for which the margin is largest. Okay, so, and we classify a test observation based on the side of the maximum margin hyperplane it lies. So what determines where we classify the test observation is a function of where the maximum margin hyperplane lies. Okay. Now let's let me look at this figure 2. We can see that, look at the hyperplane now, the margin, the maximum margin. You can look at the way it is. Now, those points that falls on the hyperplane, they are actually they are the support vectors. They are the ones that are captured for the analysis. Don't forget that we said that the test observation will be based on where the trend of observation is classified. Okay, now, all right, so like I've said earlier, now on this page, we have trend observations that are equidistant from the maximum margin hyperplane and lie, you can see that it lies on the dashed lines, indicating the width of the margin. Okay, so these particular observations are known as the support vectors. So what it implies is that we have 20,000 observations. It could just be 15,000 that are on the process supports. Those are called support vectors. So let's look at how is it constructed mathematically. When we go back to the linear programming process, you see that equation 5 says we are maximizing m, and we know that m is the margin of the hyperplane. So we want to maximize m subject to that equation 6, and we can see the left-hand side of equation 7 is a function of what has been defined earlier. Okay, so the constraint in 5 and 6 will ensure that each observation is on the correct side of the hyperplane and at least a distance m from the hyperplane. So that is what the constraints, that's what they do. Now, beyond that, we now move to support vector classifier. Now, when we look at the earlier one, look at it like I said before, the maximum margin, you can see classifier, usually have thin margin. So,
Hello, sir.
Can you hear me?
Yeah, I can hear you, but I have a suggestion, please.
Okay.
Please, can we start all over? Because of
Okay.
some of our brethren are just, our people that are just joining. Let's just start all over, please.
Fresh.
Yes, so that those that have missed the other one can also click into this. Thank you.
Okay, you mean from today's own, Abi?
Yeah, from today's own.
Okay, now, today we are looking at this, the following is the outline for today. The introduction aspect, we look at the maximum margin classifier, the support vectors classifier, the support vectors machine, then support vector regression. Actually, this was supposed to be support vector regression. It was copy and paste, not well edited. So then we also discuss the R scripts to achieve our the lab result for the lab session. Now, in this lecture, we are going to be discussing the theoretical background for the support vectors machine, after which we are going to simulate data and conduct the analysis in the lab session. Then we also apply a data set built into R to further carry out some analysis based on classification. Now, we know that this particular equation expression in 1 is we are all familiar with it, and is we have B0 plus B1 x1, that represents a equation of a linear equation, as it were. By the time you know that this y cap is equal to what? B0 plus B1 x1 plus B2 x2, as the case may be. Now, we say that the sign of equation 2 will determine the side on the hyperplane that it falls. So, assuming this is equal to 0, which is equation 2, then is directly on the hyperplane if it's equal to 0. That equation 2. B0 plus B1 x1 plus B2 x2 up to BP xp. It falls directly on the what? On the hyperplane. But if it's greater than 0, it's on one side. And if it's less than 0, it's on the other side of the hyperplane. So the sign on the left-hand side determines the side of the hyperplane that it falls, depending on negative or positive. Now, this has been shown graphically using an example, 1 plus 2x1 plus 3x2. So the value of x there will actually determine where it falls. So if it's greater than 0, it's on the blue region, and if it's less than 0, it's on the purple region, just like it has been shown here. Now, we discuss the maximum margin classifier. Now, the maximum class as a hyperplane is a separating hyperplane for which the margin is largest. That is, it is a hyperplane that has the farthest minimum distance to the training observation. Farthest minimum distance. So, and that will determine where a test observation will be what? Will be classified, will be based. So we then classify a test observation based on which side the maximum margin hyperplane lies. Okay. Now, we can see this, the figure 2 here shows that we can see the hyperplane. Now, we can see the thick line. The thick line, if it's equal to 0, then it falls on the thick line. Otherwise, it falls on either the red part or the blue part. So whenever it falls, this actually shows that there are 3 observations that falls there. We can see the blue and the red. We can see 3 training observations are equidistant from the maximum margin hyperplane and lie along the dashed lines. We can see, indicating the width of the margin. The observations are known as support vectors. So, and as provided here, the maximum margin hyperplane depends directly on the support vectors, but not on the other observation. So what it means is that when you are conducting analysis, the results, what will be computed, will be based on support vectors and not other observations. That is why it is called support vectors. Okay. Now, let's look at how it is being constructed. We know that the task of constructing the hyperplane is based on the set of n training observation. So we can see that our the p dimension, and we say it belongs to a real the set of real number with p dimension, and we can see the class. Okay, we can see that our y1 to yn is also a member of sets between 1 minus 1 and 1. And when we look at the condition following linear programming, we can see that we are maximizing m. M is the margin of the hyperplane. So that's what we want to maximize. Now, we have our constraints subject to equation 1. Then you have equation 7, which is as closely related to equation 1 and 2 earlier discussed. Okay. Now, we are now talking about the support vectors classifier. Now, the maximum margin hyperplane is not satisfactory because it has tiny margin. So the support vector is more robust to individual observations. And also it better classifies most of the training observations. And we can see that the support vector classifier is a solution to this optimization problem. We can say as provided in equation 8 to equation 11. As earlier defined, that m is the width of the margin of the optimization problem, and the aim is what? To make m as large as possible. And c is straight at the tuning parameter. Okay, and you know that our tuning parameter is usually chosen by cross-validation. Like I said, in the first 2 weeks ago, we talked about different types of cross-validation, about K k-fold, leave out one cross-validation and the rest of them. So for us to choose our C, we rely on the cross-validation. Now let's now look at the support vectors machine. Now, what differentiates support vector machines from support vector classifier is just that the addition of kernel which give room for nonlinear boundary. So, and that's what we have in equation 13. Okay, now let's look at the computation. Like I said earlier, the maximum margin hyperplane depends directly on the support vectors. For computing predictions, only support vectors are involved, not the whole training set. So this I have been said earlier. Now let's now look at support vector regression, and we can see equation 14 as provided, and our f of x, which is simple as is provided. If you multiply this, you're going to obtain 15, and that is what we have for the regression. You can see what it looks like. You can see the one on the negative side is on the lower part. The one on the right side, this is also a replicating our linear regression. So now let's go to kernel choice. We said we should use linear kernel when number of features is larger than number of observations. That is when we have a case of high dimensional data. When number of features, we can have 5,000 features, but observation may be like 100. Advice is to use linear kernel. Okay, now so that means if we use Gaussian kernel, it may be slow. Okay, and we say use Gaussian kernel when number of observation is like a number of features. That is, we have like 3, 4 features, then we have plenty of observation. I mean, number of n is high, then we can use Gaussian kernel. All right, so let's now look at the difference between logistic regression and support vectors machine without the kernel. Now, the only thing is that support vector machine is much more efficient and has good optimization packages. Okay, so that is it. So we can conveniently make choice of SVM over logistic regression because of the efficiency. Okay, and now say, why are SVMs often more accurate than logistic regression? SVMs uses kernel, but regression too can use kernel. Actually, we have kernel logistic regression, but the kernel used by SVM has been proven by author to be much more reliable. Now, SVM assume less about the model form. Logistic regression uses all the data points. It assumes probabilistic model, while SVM ignore points that are clearly correct and give less weight to ones that are wrong. Okay, all right. So now to do that, we are going to be looking at this particular one. We are relying on simulated data, and to do that, we have our libraries which are earlier been made known to you to have. We have library E1 071, HydroGov, Boots. Then the process follows that we simulate 10,000 data for that is a binary response variable. Now, number of observation, that's why we have NOPs. Then we simulate X1 to X5 from uniform distribution. Then we can now define our data as follows. Then we get our correct, which is the one of the packages required. Then we create a partition 80%, okay, for our training sets. Then for our test sets, we remaining 20% for our test sets. Then we proceed and fit logistic regression, cross-validation. We have our test MSC. Okay. Then we now use that same data for support vectors machine. Then we conduct it as follows. When we get to the lab session, we are going to be doing all this. We obtain our error, the root mean square error, and find the value of W and our B in that model, in that regression model. So before next thing now is how to tune the SVM. When you tune the SVM, it's expected to give you a better result, and that is what we have. All right. So we collect our plot. Anyway, this all right. Then we find our best model. From there, we proceed and obtain other values. All right. So then for the CAN data, the CAN data actually consists of a number of tissue samples corresponding to 4 distinct types of small round blue cell tumors. For each tissue sample, gene expression were measured and recorded. Data set consists of training sets and test sets. Okay, and as you can see, it contains 2308 genes, while the number of observation we have 83, while training observation is 63 and test observation is 20 respectively. Then we can see we need ISLR package to do that. Then we conduct all this. We can see the dimensions is 3 by 2308. Then the dimension of the text sets, we have 25. Okay. All right. So we can now see the table. You can see the classification because there are 4 different classifications for that data set. It's classified into from 1 to 4, and each class has, the first one has 8, the next one 23, 12, 20, as the case may be. And we can see the table for the tests. That's this 3 plus 6 plus 6 plus 5. That should give us 20. So that we said we have 20 test observations. So it has classified them into 1, 2, 3, 4. Now the next thing we'll do is to obtain our results. And we can see that in the training sets, there's no error, no single error, because they were all classified correctly. 1 goes to 8 observation for 1, 23 observation for 2, like that. You can see the way it is classified. So for the training observation, no single error. Then now proceed to the test. For the testing, obviously there's an error because you can see these 2 supposed to be 8, but it classified 2. Out of the 8, it picked 2 and put on that 3. So, and that is just that. So we can now move to the lab session if there's no question.
Sorry, before that, please, to everyone, can you please, there's a link on the chat. Click on that link. You can download the slide and the code so that you can follow the instructor as we are moving on. Please, there's a link on the chart. Yes, just click on that and you can download. Still here in case you need more. You can download the link and download the code with the slide. Thank you. Continue, sir.
So I can stop sharing this.
Yeah, go ahead with the lab.
So that I can share the R Studio. Okay. Can you all see my screen?
Yes.
Okay. So like I said earlier, to do that, we need packages such as E1071, IDLEGOV, Boots. Then, so the first thing we're going to do is to call this library and run, is to lines 1 to 3. We call the packages required into the RStudio. Okay, we have them now. All right. So we set the seed, that is the initial value. Like I said last week, we use this seed so that anytime we want to run it again, we'll get the same result. So we say set the seed 1. We call it, we run it. Then our binary response variable is from y, is from binomial distribution. So we can just say, okay, head. We can say head y just to see what has been imported. Because it's 10,000, it's going to be large. So let me just, so these are the first 6 observations to actually show that the values are binary. Then the next thing we do to get predictors, we have 5 different predictors. I can now just run from 7 to 11. 7 to 11. What is wrong? Okay. Knobs 0, 1. All right. Okay. We actually want to run 10,000 observation. Okay. Now, what we just need to, like, that knobs we are seeing there is telling us that we need to run 10,000 observation, and it ranges between 0 and 1. But I don't know why this is not running. It's supposed to run. Okay. This particular one does not need any package to run. It runs. Okay. What's happening? What could be wrong here? Who can figure out what's the wrong here? Okay, why is it not running? Okay. Oh, did I call 1,000 before? Oh, the reason is that I did not include the 1,000. Oh, I've seen it. Okay, so let us add the remaining lines. Okay, so we say we have been able to get our predictors, so we can call. Now, these are our data now. We can now see what our data looks like. We can say edge data. So that's make us to see the data that what our data looks like. You have x1, x2, x3, x4, x5, then our response variable. Okay. Now let's now to do that, we actually want to partition our data into training set and testing set. Now to do that, to use this function create data partition, we need package correct. So we'll have to call package correct. It has been loaded. Then we create a partition. We call it indexes. And our training data sets, we have, then our test sets, we have this, the remaining part. Then we can look at what we have, the test and the training observations. We can look at them. So that's for the response variable. Now let us fit logistic regression to the data that we just created. So we say glm.fit is equal to, and the family is binomial for logistic regression. So we have this. Okay. So this is what we have for logistic regression. Then for our prediction, we have, okay. All right. So now what you need to do next is we want to find our cross validation error. And to do that, we are going to use library boot. So we can just go ahead and do lines 27 to 29 to save time. Now, okay. Now what we have just done is to get a cross validation error. Okay. All right. So we may now want to view the cross validation error. Okay. Now, let's now have our MSC, our mean square error. We want to check what our mean square error is like. Then we run this. Something is blocking this place, this audio. Okay. So we can now say, what is happening here? Okay. Something is missing here. Okay. So I don't know what. Okay. Now we can see our cross validation error, our MSC is the 4.20 per minus 5. Okay, now let's look at this particular one. Okay, see our cross validation error has been provided above. Now look at the MSC. Then we also obtain the root mean square error as this. Okay, that's for the logistic regression. Now let's look at the SVM support vectors machine. For support vectors machine, we use that same model. All right, and our data is a training set. So we can run it. We can run our SVM. Why? Okay. So I think the R is a bit slow. So if we run our SVM model, Okay, so we can see what it looks like. Now, what it's telling us is that we have our kernel to be radial, then support vectors is 4740. And if we look at 80% of 10,000, that should give us 8,000. But this is telling us that it's only 4740 vectors are supported. You can see what it looks like. Okay, now let's look at the prediction now. We want to predict. Okay, so now we can have this. Like I said the other time, I said you predict using test sets based on the training set. This is a prediction now. This is what it looks like for each. Is actually massive, is large. So what we have just done, but here now we are not going to have the mean square error for the test sets. Then we run this. Look at the mean square error for the test sets for support vectors mentioned. Then to obtain the root mean square error, the function is also there. It also has been defined. Then we obtain 0.1784. Now we want to obtain for the support vectors regression now. We want to obtain the coefficient in that model, and that can be found in let's just run 54 to 60. Okay, so we can see. Now we know that the W represents a matrix, and in this case, it is 1 by 5, Abby. Okay, 1 by 5 because we have x1 to x5. But for the B is just look at it. Let me see. Let us print B. Where is B? Okay, this is just B. That represents the coefficient, the constant term, which is 0.1, 0.01733. Okay. Now let's tune the model. After tuning the model, we now compare to the errors of the previous one and this. So for the tune model, we have this. We have okay, it's running. Okay. Now we can see that error estimation of SVM using 10-fold cross validation is this 0.035. Okay. Now we are actually supposed to plot our performance. Okay. But before we do that, we are going to obtain the best model here. And by the time we run 69 to 70, we'll be able to obtain our best model. Now, for the test sets, it's telling us that is 1244. After tuning it, it has reduced the support vectors to 1244. Then when I want to predict now based on the best model, so we have equation 73, line 73 to 76. Then we run this 0.0311. So let's see what the previous one was for before tuning it. What do we have? Okay. All right. Let me see. Okay. Now let's look at the root mean square error. The root mean square error, we have 0.1767071. Okay. Now we're now going to calculate our parameters based on the best model. We have lines 84 to 89. We run that. This is what we obtain. And this actually is different from the previous one. Okay. Now let's look at what it is like for our training sets. Look at it. We have our training sets. We want to look at the features. Then we do this. When we do this, it will give us different the cost, the radial, and everything that we used is running. Okay, so this is what we have. But what it is telling us that for our training set is still 4740, just like we had before. Just a replica of what we have before. Then the test set, we have we also run it to see what we have is 1240, just to validate our earlier claim. Now for the entire data set, for the entire data set of 10,000, what support vectors do we have? Okay, we have this. Okay, gonna bring it up. Okay, so it's telling us that out of 10,000 observations, it's only 5846 that are support vectors. So that is what the outcome, that's what the result means. Okay, now we now want to go to a real life data set. The previous one was actually on regression, but here we are going to be doing classification. Now, to do that, we have the data set is embedded in ISLR package.
Sorry, doctor.
Yes, please.
Yeah. My name is Femi Ayola.
Yes.
Please permit me to make a contribution to what you just concluded here.
Yes.
To the class, if we look at what our professor is telling us here, I just want to relate my very little experience to the concept of the training and the test part of it, right? Go by what one is doing practically in industry. You see, the data our professor is talking about here is trying to let us see that we are going to have what we call history data that will have a very long year length. Now, when we have this kind of a history data, and we may have different models, like in the US, we have a mortgage models, we have a credit card models, we have a economy models, we have a different data set, different models. And all these, they have a different history. Now, in order for us, like what is obtainable in bank, regulatory side of it, you see the training part of the data that our professor is trying to tell us there, it's like the history data, but you want to be able to see whether that data is explaining what will happen in future that we call forward-looking. Does that model going to produce what we call a forward-looking? Now, you take part of it. Let me give instance in banking now. You are trying to build model and see what will happen in economy. There is a regulation called CICAL. This CICAL, because this is a training set, and the test part of it is what you call the in sample and out sample in industry. So sometimes we use what, like for CICAL, it's 9 quarter, because in practical, it may not be 80-20, it may not be 75-25. It may just be take best 9 quarter. Let's see how it will perform. It may be CCL, take 13 quarter and see how it works, and so on and so forth. Now, after testing it, the MSC that our professor is talking about here is just a matrix. The lower the MSC, the better our model. Once our MSC, right, and our RMSC, it's going down, because all this metrics, they are bigger, they are better and robust more than R squares. Because sometimes R squares may be giving you good results even when the data are spurious. So what I'm trying to say is this: beyond the way we are seeing it here, it is very practical. And the lower our RMSE, the better. If we look at what our professor just showed us there, we can see that after tuning it, our RMSE was better than the ab initio. And that is the essence of a tuning. Thank you so much. And thank you for giving me the opportunity to talk.
Yeah, thank you, sir. My Oga at the top. Thank you. So we have actually.
Hello, sir.
Yeah. Any other contribution?
Yes, I have a small question.
Questions?
No, I have a question, sir.
Okay, please.
Yes, sir. Please, can you shed more light on the selection of the hyperparameters like gamma and epsilon, and
Connection, please come
how
again.
they affect I said, can you shed more light on the hyperparameter selection, like the gamma and epsilon, those parameters,
Okay.
and how they affect the RMSE?
Okay, yeah. Basically, if you look at what the output, the previous outputs, where is it? I'm coming. You know, when you fit the SVM model, these things, it brings out the kernel. Actually, you choose radar kernel. Are you getting it? Then the costs, the gamma, the epsilon, those are the parameters provided initially, but these ones were actually used to now buttress and determine, that helps us to determine what number of support vectors that we have. Now, what's the cost saying? You know,
Okay,
when
so
you are doing your optimization, there's costs in optimization. Are you getting it?
yeah.
So the cost, at times when the cost can be large and the cost of doing it can be lower. And the cost is likened to error. Okay. So that is just that.
Okay.
Right.
Okay. On the values of the epsilon and gamma, like, is there a certain range of values we can select from? And then also, if we are obtaining, in the case where we are obtaining, let's say, a large value for our RMSE or MA or MSE, depending on what we choose to use. Let's say we are obtaining 16, 20, or even 64.
Okay.
How do we break them down using this parameter selection? And so is there a range of values that we can actually, play around it for this gamma, epsilon, and the rest of it?
Okay.
Yes,
now, well, this output is a function of the what has taken place. Are you getting me? Earlier?
Yes.
So, but usually in some cases we can choose epsilon to be 1. But actually, there's not really been a defined choice per se. But the interest is in kernel. The kernel choice has been the interest. And you see that the gamma actually, when you the tuning process, you determine the gamma comes out. So at the end of the day, that's why we have these values here.
Okay.
Now, kernel,
thank you very
to
much.
give you different stuff entirely. Are you getting it? So that's just it.
Okay.
Right.
Yes, sir.
So,
okay, thank you very much.
Let me see. The first, I'm coming. Let me go to the first SVM. All right. Where is it? Okay. Now, look at this, for instance. Let me run this line 39 and 40. Let's see. It's running. Okay. Do you see that here, those values were not chosen? Can you take notes?
Yes, yes.
They were not
Yes,
chosen. So, and you can see that is a function of what has taken place in the process of obtaining the support vectors. Okay.
right.
So now we have looked at our what was it called? The simulated data for regression in the case of regression. Now let's look at the live data. Now, like I mentioned earlier, when I was discussing the slide, I said it has to do with is a high dimensional data containing observations, 83 observations, training set 60, test set 20. Now, and we have features, 2,308 features. So you can see that ordinarily is high dimensional. So, and we can see that our library that we are using, that we're going to get the data from, is actually here. Okay, so now what is telling us that we have training sets, we have X set, X test, Y train, Y tests. That's a feature that we have in the data, the way the data has been structured. Then let's look at the dimension. The dimension we have 63 by 2308. Okay, let's look at the dimension for our test sets. Dimension for our test sets. Actually, I didn't include brackets here. So we can say our test set is 20 observation. Okay. All right. Now let's look at the length. We can move these together. All right. So let's see, you can see that the length for Y is 20. The table is this. For those in one classification, there are 8. The second classification, there are 23, third classification, there are 12, and 4, there are 20 altogether for the training set. Then for the test set, we have those classified as 1, 3, 2, 6. You know, those genes, there are different classifications, like I said earlier, 4 classifications. So, and that is why the classification actually were not named, but it's actually a biomedical medical data. So now we proceed from there to fit this. Now we will run line 20, line 111. We declare that as a factor. Okay, then that same that we have there, we can see that in line 112, we are already fitting SVM there. And we say our data is that. The that's already in 111. Then kernel is linear. Here, we define cost to be 10. It could be anything. We could choose any cost. You can see, we can even say 21, but here we just use cost to be 10. All right, so now when we do that, we have, okay, so look at what we have from there. Now, support vectors is 58 out of 60 because we are dealing with training set. Is 60. It also brought the parameters for us. You can see linear, you have a cost to be 10, which was already defined. The support vectors, that means 2 vectors are not supported. That is for class 1, we have 20, class 2, 20, class 3, 11, and 7. So number of classes, like we have earlier, is 4. 1 to 4. Then we run lines 115. Now, this has already been explained in the PowerPoint. We can see the training set. You can see that correctly classified in all the cases. Okay. Now, 8 goes to 1. All other ones are 0. 1, 2 classifications are 0, and this. All right. Okay. Okay. So we can see the way it runs. Now, data.frame already does set up our data, declare as factor, can, white test, and all. Then that same thing that we declare in 117, we'll put it here as our new data. You know, the previous one was actually training set. That's why. So, but here we declare as new data now. So now what we obtain next, we have this. This is already in the slide. We can see that there's a kind of little error there, and the only error there is classifying 2. Instead of having 2 under 2, there we have 2 under 2, then 2 now goes to 3. So that's actually a wrong classification. So
sorry, for SVM in line 112,
okay,
is telling us error here. When I try to run it, it's saying we should not define, we are not defining the SVM. So can you comment on that?
line 112. What I have here, do you have exactly what I have on the screen?
Exactly.
I don't know what could have gotten, what could have been wrong. I don't know.
It's just complaining about the SVM. Is there error in SVM? Could not find SVM. I don't know.
Yes, the reason is that the package required, I maybe not loaded.
Which of them?
E1071.
I did that. I did.
You have it?
Yes, I have it. It
What
showed me
about
the
all the packages? You have them already loaded?
everything. Yes.
Oh, so what could be wrong? I don't know, but
Just continue, don't worry.
yes. So now basically, this is what the output is like. So that's with this now, we could apply just like Professor Ayola said. So machine learning support vectors machine is applicable to all kind of data. This is just an example of medical data and a classification problem. So if you have finance data, stock data, and many more, you can equally apply the model. And at this point, I will now leave you to explore more in this area. So this is where we draw the curtain as per the class per se. But if there's anything we have, any point you want to raise, any contributions or any questions, is welcome.
Okay, thank you so much. If you have any question, please raise up your hand. You can unmute yourself and ask the question. Then, apart from that, is there a particular things one need to look into when it comes to support vector aspect? How do I know that I need to use it?
Okay. Well, to know, like, in support vectors machine is applicable to regression and classification. Now, you see, when our data, it is actually applicable to big data, because I can even share a paper with you where I use logistic regression and support vector machine. In that work, when I did the plots, they are almost at par. Why? Because the number of observation is actually low. But by the time you have big data, like a 10,000, 20,000, 50,000, like look at this, like I mentioned earlier. So it's advisable to use a robust method such as SVM for it. But if you have low data like that, you could use logistic regression. That is it. And you know, like I mentioned earlier, the logistic regression or other forms, they don't consider non-linear boundary. SVM is robust to both non-linear and linear at the same time. The introduction of the kernel helps to take care of the non-linear aspect. And there's also provision for tuning our model. So by look at all the provisions provided in SVM, you would see that, well, I think this could give me a better result if I employ it. So, and that is why I think it is more suitable in the case where we have large data sets. Big data.
So it simply means on the big data, that's where the SVM is applicable.
And it's applicable anywhere. The results with other methods, the difference may not be much. Because you can see that, you know, when you look at the rigor involved in fitting SVM, you may say, okay, as long as, you know, let me just go for the alternative. But if the objective is to ensure that, well, you do something, you know, in this process now, we have the training process where you train the computer to give you a prediction with minimal error. That is where you employ the machine learning approach. The system has already been trained to do the right thing. But in the other process, there's no process, there's no involvement of that. You just put it in, you get an output, and you move. Are you sure that the observations you have there are supported for the analysis you want to conduct?
Okay, thank you so much, sir. Yes, any other contribution, any other question?
And thank you so much.
We have Dare Julius Remy. Over to you, sir. Oma.
Good evening over there. My name is Julius Dare. I just want to ask a question. My question has to do with the type of regression structure our professor just used. And I want to know, if I use a different regression structure, like what we call the GLMM, which is the combination of GLM and LMM, I want to know if we're going to have a better predictive ability, as in, when you are now comparing with the SMV, are we going to have a better fit? As in, when we compare with the GLM that is being used? Because based on what the explanation that has been made so far, I discovered that the GLM is used against the SMV. What about if I use a regression structure that combines both the LMM and the GLM? Are we going to have a better prediction compared with the SMV?
Okay, SVM. Okay, thank you. Well, basically, like I did, like, don't forget that when you look at this place, when I started with the regression, we have, let's see, you can see that look at lines 23 down is actually a GLM structure, right? And this is just logistic regression. Okay, now we can see that both SVM and GLM, they have their strength. Are you getting me? And they have where their shortcomings. Again. So, and to know that, we can explore the literature. Are you getting it? You can explore the literature, but as much as I know that SVM actually provides a more robust alternative. and it contains in what I've done before, and one can equally explore other literature and see what they have to say about it. And that's it. And you know that even in the GLM or whatever model, even regression model, there's machine learning provision for them. You don't just, there's the normal one, the general one that is known, that you just put the model, then you get your result. But in the provision, in machine learning platform, you do what you call cross-validation. Are you getting me? So when you do cross-validation, when you do your, so that it will help you, is a process of, is a way of training the computer to know what to do with minimal error. So when you are talking about regression on a normal classical way that we know, it will give you result actually. But following the machine learning approach is different ball game entirely. And that's just it.
Thank you very much, my prof.
Yeah, we thank God.
Thank you, sir.
Yeah.
Any other question? Before we call it a day, any contribution, addition, subtraction? Okay. The absence of no contribution, we will share, or let me quickly share with us for those of us that have missed the previous edition, you can just check some of the videos of what we've done so far, so that you can download or watch them on that particular channel. So it will help us to be able to, from there you have access to others' material. I just put it on the chat. So if you are interested to see the first section, the second section, and the last one, this particular recording also will be there anytime from now. So, Dr. Olumide, the next class will be next Saturday, right? Is it next Saturday or I'm not too sure.
Yes, we'll communicate.
We'll communicate with you, with everyone. Don't worry, you will get our.
Hopefully next week, but if otherwise, it will be made known.
We'll communicate, no problem. Yes. Then also watch out for the Python edition. I discussed with Dr. Taiwo, and he promised to put some things together for us. If you are not sure of how, then you can wait for the Python. The Python will be available very soon. So we will also roll out the adverts. You will see the flyers, and we encourage you to join and invite others. So if you have any other things to say, Dr. Olumide, over to you, sir.
Well, no other thing for now, but my advice is just that you lay your hands on so many things, get data, live data, the data are available online. So just lay hold on them, and do some work on your own. And I believe if you do that, then you improve yourself more. And that's just it. So if you have any questions, you can always relate to us. We are available. Thank you.
So on this note, we'll call it a day. See you guys next time. Bye for now.
Okay.
You are welcome, sir. You can drop your, yes, thank you. Ajiboye, thank you. Odebody, thank you. Dr. Emeka, you are welcome.